Hello and welcome to this video. My name is Michal Forisek, also known as misof. I am one of the organizers of the IPSC contest, and in this video I'm going to talk to you about problems that involve sound processing, such as the problem K from IPSC 2015. The first thing you need to understand is how sound works and how our ears process sound. Sound are basically vibrations in the air. These vibrations hit on your eardrum and then this makes the sound in your head. The frequency of these vibrations is the pitch, so the faster it vibrates, the higher the sound you hear, and the intensity of these vibrations is the volume. So if the air vibrates more, then you hear it louder. And now if you have a speaker connected to your computer, the speaker has a membrane, and the membrane produces sounds by vibrating exactly in this way. And whenever you have a sound file that is stored in your computer, it describes these vibrations as well. So it describes how the membrane should vibrate to produce the correct sound. So now we are going to take a look at a specific problem K from IPSC 2015. In this problem, the problem statement tells us that there is a wall and there are some bells mounted onto the wall. The bells have different sizes, and the size of the bell, which is also the pitch of the bell, determines the height where it is mounted. And what we are given as the input is a recording of these bells, and we have to use the recording to determine the positions of individual bells. Now the first thing to do in order to solve such a problem is probably to get a sound editing program such as Audacity, which is what we are using here. So fire up the program, open the easy input, and you should see something like this. So what is going on here? What you can see here are kind of triangles, and these triangles represent the sound. We can actually try playing some of it. Okay, so it is actually sound. So let's go over what we can see here in the window. First of all, you may notice that there are two rows. The rows are called channels, and they are what your ears hear. So the first channel is what is going into your left ear, and the second channel is what goes into your right ear. And you may notice that they are different, so this is then used to create the illusion of a sound that is coming from different directions. If you hear something louder in your left ear and less loud in your right ear, then you think it's coming from the left. The next thing we need to know about is volume. In this editor we can see volume shown as the size of these triangles. So the farther away from zero the sound wave goes, the louder the sound will be. For this highlighted bell, you can tell that this has to be a bell that is somewhere on the left side of the wall, because the sound that goes into the left ear is louder than the sound that goes into the right ear. Okay, now we are ready to take a look at the entire row of bells and to verify whether what we know is correct. So here I'm highlighting the first row of bells. These are all the bells with the same pitch, as we will see later. And as we are going from the left to the right, then we can see that the amplitude for the left ear and also the amplitude for the right ear is first increasing as we are getting closer, and then decreasing, and the maximum for the left ear is reached sooner. If you look at the very beginning, at the first bell, you can see that you hear something in the left ear but nothing in the right ear. And if you look at the other end, then you can see it's symmetric, then you still hear something in your right ear but not in the left. Now the last thing we need to understand in order to solve our problem is the pitch, the frequency. And in order to understand this, we have to zoom in closer on these sounds in our editor. And this is what we will see once we zoom in close enough. If this were a pure sound, just a single note, then you would see a nice periodic sine function here. But as this is a real-life bell, then there are some other oscillations, some other vibrations that distort it a little bit, but still you can see that this is a function that is more or less periodic, and the period length is what determines the pitch of the sound. Alright, so now we do understand what it is we are seeing here in the editor, But how do we solve our problem? Well, one of the things you can see in the sample solutions is what I did here when test solving the easy input. I simply copied this waveform from the sound editor into a graphics editor so that I have the information preserved when there is a bell, when there is no bell, and then I just copied and pasted the individual rows of bells below one another, and this graphically produced the solution we needed. We can also do it completely manually from this file. If you just zoom in at the beginning, you can see that each of the bells is precisely 1.5 seconds long. So here at the beginning there is a silence. Oh, sorry, this is the beginning. So at the beginning there is a silence. So this is a 0, then there is a 1, another 1, another 1, another bunch of zeros. We can count exactly how many, and so on. So I'll just grab pen and paper and I will paint the picture manually like this. But obviously this was not the intended solution for the hard problem, although I think it's still possible to do it completely by hand. It is easier to let the program help you. So in order to process this algorithmically, first of all we need to split this audio file into segments of 1.5 seconds, and if you don't know how to do it, just Google a tool for it. There are plenty of those. And then we can process this separately. For the easy input, the only thing we need to determine is whether or not it is silent, and for the hard input we need to determine the amplitude for the left ear, for the right ear, and also the frequency. So how can this be done from a program? Now obviously the easiest solution is to find a library that can help you. If you take a look at the sample implementation, you will notice that we are using the Fourier transform, for example, to determine the frequency of a sound. But in this case, everything we need to do is so simple, we can actually implement it from scratch very easily. And now I will explain how to do so. You will need to understand one more thing, and this thing is sampling. Now I will zoom really closely onto the wave function in the editor. And now you may notice that there are dots on the wave function. So what is this? These dots actually represent samples. If you take the MP3 file and you convert it into a waveform file, the file with the WAV extension, what you will get is a pure sequence of values. Each of these values is the vertical coordinate of one of these dots in order. So it's just a sequence of displacements of the membrane of a speaker. The important thing to notice in the editor is the sampling frequency. In our case, you can see this is the 44,100 Hz. This means that 44,100 of these samples represent 1 second of sound. If you want samples of length 1.5 seconds, multiply that by 1.5, and this is the number of samples that is a single bell sound or silence. So you take the waveform file, you split it into segments of this length, and then you can process each of these segments separately. Obviously, to detect silence, all you need to do is to look at the absolute values of these numbers in your segment. If all of them are small, this segment is silent. If some of them are large, then there is some sound. And the magnitude of those numbers is actually telling you the amplitude of the sound. So the higher the numbers, the louder the sound in this interval. The very last thing we need to determine is the pitch of the bell, so the frequency of the sound it makes. So what we are looking for here is the shortest period of the waveform function. Probably the easiest way to determine it was to realize that these are bells from a musical instrument, and they are actually tuned to some of the musical notes. So if you just try the shifts that correspond to those notes and verify which of them works best, you are done. But even without this realization, you could simply solve the problem by brute force. The range of reasonable frequencies is not so high, and for each of them you can verify how well it matches the data you have and choose the best one. Alright, that's it for today. Hopefully you had fun watching this video, hopefully you learned something new, and make sure to join us for IPSC 2016.